Hello and welcome back to Advent of Code 2019. Day 7. We're on to day 7. So yesterday I did days 1 to 6. Quite a few days in one session. That's good progress. So I might actually be able to get through this whole month within a month or so. Let's just check the YouTube stream is working as well. Okay, cool. Right then, let's start. Day 7. What have we got? Looks like something to do with some sort of simulation, like game of life type thing. All right. Let me grab my copy as well. Okay. All right. Day 7, amplification circuit. Based on our navigational maps, you're going to need to send more power to your ship's thrusters to reach Santa in time. To do this, you'll need to configure a series of amplifiers, electronics things, increases the magnitude, already installed on the ship. There are 5 amplifiers connected in series. Each one receives an input signal and produces an output signal. They are connected such that the first amplifier's output leads to the second amplifier's input, okay, and then it goes to your ship's thrusters. The elves have sent you some amplifier controller software. It's a bunch of integers, okay. That should run on your existing int code computer. Oh, here we go. We're using the one from day 5, are we? Alright. Well. Okay. It's going to be a lot of assembly code this month. It's fine. It's interesting. Tough, but interesting. When a copy of the program starts running on an amplifier, it will first use an input instruction to ask the amplifier for its current phase setting. From 0 to 4. Each phase setting is used exactly once, but the elves can't remember which amplifier needs which phase setting. What? Okay. The program will then call another input instruction to get the amplifier's input signal, compute the correct output signal, and supply it back to the amplifier with an output instruction. Okay, so the program acts as the amplifier's logic, essentially. Okay. Your job is to find the largest output signal that can be sent to the thrusters by trying every possible combination of phase settings on the amplifiers. Make sure that memory is not shared or reused between copies of the program. Okay. don't really understand. Suppose you want to try the phase setting sequence 3, 1, 2, 4. So there's only 5 of them, are there? Okay. And it has to be some permutation of 0 to 4. They're not allowed to use the same ones. So that reduces the number of possibilities. So we set A to 3, blah, blah, blah. Okay. So start the copy of the amplifier controller software that will run on amplifier A. Provide it with the input 3. And then the second input, provide it 0. Okay, so input is going to have to be supplied as a sequence, as a generator, I guess. All right, we can figure that out. So when you get to B, you give phase setting, and then whatever output signal was produced from A. I see. The input signal 0. So we start with 0. We input 0 to begin with, do we? Yeah, okay. What is the highest signal? So we've got to try all permutations that can be sent to the thrusters. And the final signal... Okay, will just come out of E. Okay. Sort of get it. So we're going to have to copy the program code from 5. This huge chunk. So it's actually a good thing that we cleaned it up a bit, because I'm going to be using it again. We'll have to change the name to, let's change it to run int code. More descriptive. And the inputs are going to have to be, well, we'll figure this out. Okay, and the program okay, make sure that can actually run. All right, so let's figure this out. So we need We don't need to modify. Well, we do need to modify. We need a series of inputs. So as inputs is going to be like a sequence. So instead of imp. So when we call imp, it's actually dot next. Imp is a generator. I forget, is this... Oh, wait, we'll find out if this works. Alright, so we test it out. So let's try running the program with say, 0, 0. So that's 0 is the phase setting and 0 is the natural input. Alright, so, and then it's going to be run int code. And then what is it? Star imp that provides it as arguments. One positional argument, but 2 are given. I don't know how this works. Do you put star there? Okay. Code. Let's convert that to a list. Tuple has no object next. No, that's not how we do it. Don't put star there. Run int code takes exactly what takes one positional argument with 2 are given. All right. How do you turn a list into a generator? Maybe I just don't understand generators very well. Oh, iter. Probably wants an iter. So we want to do like this. Iter imp. It's iterable, not generator. Iterable is what you call next on. List iterator object has no attribute next. So, how do you call next? Oh, you don't do it like that. You do you do it like this. We get 9. Okay, it works. And this is the more generalized, this is the more correct program because it uses any number of inputs, essentially. All right, so what do we do with that? We have to... First, phases. Okay, so we need iter tools. Input permutations. So is this how you do it? Yeah, okay. So basically we say, for P in permutations, so we permute all possible phases of these 5 things. Param2 is going to be set to 0, but it will change. For param1 in permutation, oh no. P in permutations. Okay, so this is 1 permutation. And then we do for I in range 5, we will need to go through each of the machines one by one. Param1 is going to be the phase. Param2 is fixed. Right. So let me replace param2 with run encode iter it's gonna have to be param1 param2 like that. So after this we should have print param2. We should just get a whole bunch of param2s. Output how do you, so it's a generator of 1 object. How do you extract whatever is in there? There's probably an easy way to do this. Python get from single element generator. We'll just get the next. Oh, well, you could probably do next, right? Like this. Okay, and the numbers get... Whoa, bloody hell, the numbers get huge. That's worrying. So what are we trying to do? We're trying to minimize? No, the highest signal. For every combination of phase settings in the amplifiers, what is the highest signal that can be sent to the thrusters? Doesn't look right, does it? That's too big. Wait. No, what do we do with that number now? So that's the final output. No, the numbers shouldn't get that big. Because it wouldn't be like, you couldn't really write it in C++ and stuff like that easily. Am I using the correct phase? Param is that, yeah. So P and permutations. Wait, that should be for 1 permutation. There we go. That's safer. Okay. Max signal equals 0. Max signal equals max of max signal param2. There we go. Print max signal. 38834. Correct. It's no good. In this configuration, the amplifiers can't generate a large enough output signal to produce the thrust you'll need. The elves quickly talk you through rewiring the amplifiers into a feedback loop. Uh-oh. Uh-oh. Now we're getting into dangerous territory. How do I see... Why is it playing it from the start? How do I see the live video? I want to see what it looks like on YouTube. Still don't get how this YouTube thing works. Hello, DJ. It's going alright. I just did part 1 of this thing, which is like a... It looks like there's going to be a lot of assembly code problems in this set, because it's our 3rd assembly code problem, and it builds on the previous 2. So it's like a continuous thing. You need the code from the previous problem to do it, which is, well, it's interesting. It means you can do interesting stuff, but it makes it tough because you can't afford to make any mistakes in any of the previous parts. So we've done part 1. So now we're doing the same thing, but we got some sort of feedback loop. Alright, so most of the amplifiers are connected as they were before. Amplify A's output is connected to amplify B input, and so on. E is connected to A's input. Alright, so it's like an infinite loop. I have a feeling we're not supposed to simulate the entire set of steps. In feedback loop mode, the amplifiers need totally different phase settings. Integers from 5 to 9. Okay. These settings will cause the amplifier controller software to repeatedly take input and produce output many times before halting. Uh-oh. We're gonna have to have cues. This is an interesting kind of problem. I don't remember doing something like this before. It's like we're gonna have to put stuff on the queue for these machines to take off the queue. Like, this is real stuff. Like, this is how real programs work. But you don't normally have like puzzles based on this because it's quite complicated. But I guess that's what we're doing now. So I see. Alright, I have an idea how to do this. Eventually the software on the amplifiers will halt after they process the final loop. When this happens, the last output signal from amplifier E is sent to the thrusters. Your job is to find the largest output signal that can be sent to the thrusters, using the new phase settings and feedback loop arrangement. So how do we know when it stops? When there's no more output. Wow, okay, this is interesting. This is I mean, this is a good use of Python generators, which is I guess what we want to do here. So you want to wrap up one feedback loop as one function, do we? So you want to initialize. All right, let's see. How do we do this? For P in permutations, so for each permutation, so that's part one. All right. Actually, let's change it to use queues, because we need to continuously put things on the queue. So we're going to have from queue import queue. So for each machine, we want to initialize a queue. So we want to, oops. So the queue is going to be a new queue. We want to put the PI on the queue. And we want to supply and we don't want to run them yet. So we just initialize them. We put them on the queue, and we need a variable for the machines, or whatever they're called, amplifiers. So the function, running function, will be added onto this, and instead of parameters, we'll just apply the queue. So when it needs inputs, it'll take it off the queue, and those queues can be. Oh, we're gonna need a queues list as well. So okay, but this can be simplified. Let's say amplifiers equals run code on the queue in range 5. Okay. So we've created 5 queues. We've run 5 machines on those queues, but those machines are halted. When we want them to run, we'll tell them to run. For now, they've been given each of those queues as input. There's nothing on the queues. Well, we can put something on the queues. We can just put P I. Why is it capitals? P I range 5. Okay, so we've got the phase, got the machine running on the queue, but it's not doing anything. It's just stationary. Okay. And then to actually trigger them, we want to do queues 0 dot put, just put the number 0 on the first queue. All right. Then for each of the, then we run each of the machines. Okay. Okay, so for I in range 5, so we put all right, signal equals 0. For I in range 5, we're going to put queues. Just put the signal on that queue, and then replace our signal with the amplifier that's using that queue. So we just call next, and then after that's done, signal should be whatever's the final amplifier's output. Max signal equals max of signal and max signal. Now hopefully we get the same result. 38834. Queue object. Oh yeah, because we need to change this to not use queues anymore. Okay. Stuck in a loop, huh? That shouldn't happen. Class int does not define get item, so P is a... What? So for one permutation, so do we get here? Yeah. So if we... So we put the Q on the signal. Signal equals next output from amplifiers I. Do we get a signal? So the probable cause of this is the... So it's possible that Q is empty at this point, which will cause it to hang forever. But we're hoping it... Oh, you need 2 parameters. Hang on, how does this work again? Ah, of course. I didn't put the second parameter on. So the first parameter is always the phase. Ah, of course, I didn't put the phases on. Run QS. This should have the phases. Q... What does this do? This doesn't even do anything. I don't think that creates a Q with that on. So we want... for Q for I in range 5, Q's I dot put P I. There we go, 38834, nice. Okay, that's just rearranging part 1, but that's gonna be very useful now. So now we've got machines that can run indefinitely in parallel, and they can be started and stopped, and they can continue progress from where they left off. This is a pretty... It would not be easy to program this in other languages like C++ and stuff. This is where Python's generators and like yield command are immensely useful. And it's not something you get to practice much because they don't normally make puzzles that use this stuff, but they should. Because it's good stuff and it's relevant. Like this is real like parallel processing. Okay, now it's not parallel processing, it's what's the term? Concurrency. It's like it's not running 2 things simultaneously. Instead, it's doing 1 step of one and then 1 step of another and so on, going back and forth, which is very useful if you want to get certain results that are mathematically accurate and you're not letting one program get ahead of the other. Okay, so now how do we do part 2? We just got to do that, but it's got to be in a cycle. One loop. given a signal and a bunch of amplifiers, we basically do this. So let's assume we've already got cues and everything. Oh no, okay, we're gonna need a bunch of cues. You got a signal, input signal, you got a bunch of cues and a bunch of amplifiers. These are being pre-processed and they're already running. In this case, we do I disconnected. Well, I'll just wait for it to reconnect. So in this case, we all right, we're back online. So we put the signal on the cue. Basically do this. For IM range 5, put the signal on the cue, and then the signal is going to be the next operation. And then return the signal, right? So we can put this, we can actually move this up here. Like that. So instead of this, we can just say signal equals one loop using a 0. The stream did go down. It should be back up now. Zero, and then just supply the cues and the amplifiers. All right, do we still get the same result? No, we don't. Why? Just took Twitch showing me like 20 ads. Oh, okay. Signal equals, we do one loop of supply 0. Ah, I see. Because it's not changing the signal, so we need that. Why am I returning? Oh, that should be returning out of the loop as well. Okay, try that. There we go. Okay, so part 1 is still correct. Now we can do part 2. So initialization is the same as before. But the permutations this time are going to be... Damn it, did I disconnect again? Alright, I'll just keep programming, but yeah, the stream seems to be down. Again, I might have to stop the stream after this problem then. It doesn't seem like it's stable right now. Alright, amplifiers. So the phases are going to be 5 to 9. Stream went down again. I don't know. If it keeps happening, I'll just have to finish after problem 7. Seems a bit unstable right now. And I am streaming to both YouTube and Twitch, so I'm using double the bitrate, but that wouldn't cause it to go down altogether. It would just cause me to drop frames in the worst case, so it seems like it is just dropping. Alright, anyway. I'll keep programming even if it goes offline. So this has got to be range 5, so including 9. Initialize the cues, put the phasers on, initialize the amplifiers. Alright, now, what we do is we do loops. And we keep doing loops until we can do loops no more. So, while true. Alright, so we start with signal 0. Signal equals, we do one full loop using 0. Using signals specifically. Oh, we're down again. Okay, I'll just finish this problem off and then we're done. Oh, this should all be in here. Okay. And print signal. Now the problem is this is going to get stuck in an infinite loop. I need to know how to break out of this, but let's just see if it actually does what I think it's going to do. Stop iteration. Interesting. So that's kind of good. So if we break out of this while loop, I think we should do a try. Now you shouldn't do this, all right? But I'm just lazy and I'm just gonna do this. Do a try. What is it? Try else? No, try. How does it work? Try catch. I don't know how to do tries. Let me look this up again. This is basic stuff you should know. Looks like the internet is actually down. It's not just the stream, for fuck's sake. Alright, can I just please finish problem 7? And we'll close the stream after. Try... Oh, of course, you could just hover over. Try... It's gonna be try else, isn't it? Why is it indent like that, though? Shouldn't it be here? Like that? don't know how to use tries. Try, oh, should be using except. Yeah, I'm using broad clauses. Sue me. All right, except break. So if we break out of this, then signal is whatever the best signal was. So just put this. Max signal equals 0. And then just do that for every permutation. And then what? Print max signal. We shouldn't be printing all this. And there we go. Is that the result? The internet's off now. Let's try disconnecting and reconnecting. I just want to see if it's the answer. Okay, I think we might be back on. Let's quickly get this done before it goes off again. We don't even have any music on. All right. Okay, submit. Correct. Okay, problem 7 done, and let's just finish the stream there because apparently the internet is not compliant today. That was a really nice problem actually. I thought that was good. It was clever, and okay, it used code from previous problems, but it could have been written as a problem, a standalone problem, just given a simplified program, because the program itself doesn't matter. It's just a thing which takes an input and spits out outputs. What matters really is that they're treated as black boxes and you do this loop process. So they could have just given a simplified program and it would still be equally difficult a problem. And it's pretty hard to code this in C++ or something because you need to use queues from first principles really. Or, I don't know what you would do. Python using the yield statement makes it a lot easier. So yeah, it looks like the internet is kind of wavering, so I won't continue the stream today, or now for now at least. But that was problem 7 done. Nice problem. Let's have a look at the old leaderboards. Yeah, cool. What else? Stats for problem 7. Took them quite a long time to complete it, actually. That's surprising. I mean, if you've already got the code for 5, I don't think it would take you that long if you understood the feedback process. You just got to write it. They might be doing something crazy, like trying to use C++ for it, which would be... I don't know how you go about doing that. 30 minutes. How long did my stream take? About an hour. But I think I could have beaten that if I was going in speed mode. Just about. All right. Well, next time we'll tackle problem 8. We can take a sneak peek. Image. Something about an image. Wait, it looks like the stream is a bit more stable now. Should I risk it? I don't know. been stable for the last few minutes. Yeah, let me open chat again. Maybe I'll risk it. Alright, we're on problem 8 then, I guess. Alright. The elf spirit, space image format. The elf spirits are lifted when they realize you have an opportunity to reboot one of their Mars rovers, and so they are curious if you would spend a brief sojourn on sojourn. What is that word? Temporary stay. How do you even pronounce it?
Sojourn. Sojourn.
Sojourn. Learning new words from this. You land your ship near the rover. When you reach the rover, you discover that it's already in the process of rebooting. It's just waiting for someone to enter BIOS password. The elf responsible for the rover takes a picture of the password and sends it to you via the digital sending network. Unfortunately, images sent via the digital sending network aren't encoded with any normal encoding. Instead, they're encoded in a special space image format. None of the elves seem to remember why this is the case. They send you the instructions to decode it. So you're sending an encoded image, and we want to decode it. Okay. Images are sent as a series of digits that represent the color of a single pixel. The digits fill each row of the image from left to right, then move downward to the next row, filling rows top to bottom. Okay, sure. Each image actually consists of a series of identically sized layers that are filled this way. So the first digit corresponds to the top left pixel of the first layer. The second digit corresponds to the pixel to the right of that on the same layer, and so on until the last digit, which corresponds to the bottom right pixel of the last layer. Okay. So one row represents one full frame. Given an image 3 pixels wide and 2 pixels tall, the image data here corresponds to the following image layers. Okay, got it. So that's our image. The image you received is 25 wide and 6 tall. To make sure the image wasn't corrupted during transmission, the elves would like you to find the layer that contains the fewest 0 digits. On that layer, what is the number of 1 digits multiplied by the number of 2 digits? Okay. Easy part 1. I think it's just showing that you can deal with matrices and unpack things via row and column and convert to and from a single vector to a 2-dimensional grid. Okay, I think we can do this. So I just shut down the IDE. Okay. Okay, so what are we doing? We want to... okay, just take the input. Okay, digits equals, or just call it data equals int x for x and f dot readline split. No, not split, just f dot readline. Let's just strip, but split. Takes all that. I think we also want to reverse it. So that we can just take from the front and it will be efficient. So they said 25 wide and 6 tall. Width equals, or should we just say M? NM equals 6, 25. Size equals n times m, I suppose. That's like how many in one frame layer. So we're going to create a list of layers. Num layers equals we don't even need to reverse it. Let's just leave it alone. Num layers equals length of data divided by size. That's how many layers we're going to get. Okay, so for that in range num layers, we want to create one layer. Okay, so to create one layer, we create a matrix of, so it's going to be okay for so it's going to be so we need to take data. So we've already used size times L already. So that's the offset now. Plus, so data. So what is the next row's data? It's going to be I times M plus J for J in range M for I in range M. It's a bit of a mouthful, but that's basically saying we range over all the rows, and within a row we range over all the columns, and then at the grid, the individual cell level, we're basically saying we take from data, we offset by the amount of the number of the amount of layer that we've already done, which is going to be 1 layer multiplied by L. Because if L's 0, then that's nothing. There's no offset. But we add in the number of rows we've already processed, which is going to be... we offset more by the number of rows that have already been processed. So for each row, we basically spend M to move on to the next row. And we offset by J because that's the column. And that tells us where in data we get the right place. Just hope this is correct. And that gives us one matrix. So layers and try printing. I don't know. Print layers is gonna be full of stuff, but going out of range. Oh, I've got too many brackets here. Oh, no, that's right. We're gonna have to test this. So we've got one layer out, I think. Why have we gone too far? Size times L. .625, is that right? 25 wide, 6 pixels tall. It's probably this index is not right, but what's the problem? So what would it be in the maximum case? Oh, fuck. That should be N. Okay. We got, I hope, 2 layers there. It should have size 2. No, not size 2. It should have size whatever num layers is. 100 layers, okay. Alright. Assume that's right so far. So, the elves would like you to find the layer that contains the fewest 0 digits. On that layer, what is the number of 1 digits multiplied by the number of 2 digits? Okay. So let's make a method. Layer count num. So basically, return sum of row dot count num or row in layer. It's just, I don't know, convenient. Alright, so, part 1. So we want to find the one that is the fewest 0 digits. Okay, so... so let's say min 0 equals the minimum of layers, key equals lambda L maps to, so given a layer, the minimization metric is going to be layer count of that layer with the 0. That's why we're making layer count, it's just more convenient. And that gives us the layer. Just call it min 0 layer, just to be clear. Print, and then we're going to have to do layer count min 0 layer ones times the number of 2s. Lots of nice Python stuff that we've got. List comprehensions, minimization stuff. 1935. Correct. All right, now what? Now you're ready to decode the image. The image is rendered by stacking the layers and aligning the pixels with the same positions in each layer. Hang on. Stacking the layers. And aligning the pixels with the same positions in each layer. The digits indicate the color of the corresponding pixel. 0 is black, 1 is white, and 2 is transparent. Okay. The first layer in front and the last layer in back. So if a given position has a transparent pixel in the first and second layers, a black pixel on the third layer. Oh, so it's what you see. Then the full image can be determined by the top pixel. What is the message produced after decoding your image? Sure, I can do this. Doesn't seem hard. That's a nice problem. It's going to be an actual picture. Okay, so we've got our layers. So we want to create a new layer. Final image equals just do that. So we've got a blank image, and then for I in range n, for j in range m, we're going to determine what the this pixel is going to be. So we can say color equals will it ever be transparent fully? We don't know, but let's assume it could be. Color equals 2, and until we find a 1 or a 0, Um, we need to make this a bit more visible. Should we say? Should we say by default? By default, it's going to be empty space. All right. No, not even that. By default, it's going to be a cross, because I don't think we'll get crosses, so we'll figure out what to do if we get a cross. All right, so and we'll say white will be empty space and black will be a hash or something like that. I think that might be quite visible. All right, so for I and J, for J, we want basically for layer in layers, if layer ij is not equal to 2, then final image ij equals, let's say, hash if it was black is going to be hash, yeah, black. If it was, so black is 0, else, because I think white will be like the background. Break. So we break out of this for loop. For layer and layers, if layer goes to layer, yeah. And that should fill in every image. And then for row in final image, print, just join it up and print it out, and let's see what it looks like. Oh, what is this? Oh, okay, I see it. To kind of squint my eyes a bit. CFL. I mean, can I do this without squinting my eyes? Is there a way to... Oh, we're leaving too much space between the lines, aren't we? Can we... Whatever, I'll just squint my eyes. CFL. Actually, change them around. Make this... It looks like it's white on black. Do that. There we go. CFLUL. No, there's no way that could be wrong. How would we get a different message? Okay, CFLUL. CFLUL. It would be interesting if they identified one way that people would do it wrong and they actually gave a different message. In that case, that would be really funny. Like if you did the reverse, the opposite way around from the layers. Should we try that? I wonder if that's an Easter egg. You get a different message if you go from the back. How would you do that? You just say, just do this, -1. No, that's not a message. Thought it was at first. It would be funny if there was one. Okay. Uh, that's it. That's day 8. That was a nice problem. The stream didn't go down once during that problem, so I guess let's keep going. We're on a roll here now. 9. Sensor boost. You've just said good. Oh, what's this going to be? Oh, it's more ink code. Oh my god. More ink code. Okay. You just said goodbye to the rebooted rover and left Mars when you receive a faint distress signal coming from the asteroid belt. It must be the Ceres monitoring station. In order to lock up onto the signal, you'll need to boost your sensors. The elves send up the latest boost program, basic operation of system test. While boost, your puzzle input, small programs, but why? Okay, let's see what that's about. Is capable of boosting your sensors. For tenuous safety reasons, it refuses to do so until the computer it runs on passes some checks to demonstrate it is a complete encode computer. Your existing encode computer is missing one key feature. It needs support for parameters in relative mode. God. So we're using the code from 5. Parameters in mode 2, relative mode, behave very similarly to parameters in position mode. The parameter is interpreted as a position. Like position mode, parameters in relative mode can be read from or written to. The important difference is that relative mode parameters don't count from address 0. Instead, they count from a value called the relative base, which starts at 0. The address a relative mode parameter refers to is itself plus the current relative base. When the relative base is 0, relative mode parameters and position mode parameters with the same value refer to the same address. So it's an offset, and it changes, and it's just one offset for the program. So given a relative base of 50, a relative mode parameter of -7 refers to 50 minus 7. Okay. And we're gonna actually show how you change the base. Okay, that's not too bad. No, we need more. We need more. Alright, before I do anything, do we need to handle multiple inputs and outputs? Well, whether we do or don't, I'll probably just use our Q-based code from now on. So let's start by just doing that, sorting out opcode 9. So we're going to copy 7. It's getting more and more complex. That. Okay. We've got our it's the same format as before. Okay, let's make sure that runs. Okay, So IP equals 0. So now we've got this thing called relative base, and it starts at 0. Okay, starts at 0. Get val. If mode is 0, we return pnum. If mode is 1, we return num. Elif mode is 2. See, I don't like the fact that we're adding these. Zeros. Oh, I suppose it's fine. Elif mode equals 2. Return. So what is it? It's going to be similar to position. So we do, instead of pnum, it's going to p num plus relative base. Okay. And then we've got a new opcode. We've got 9. What does it do? Adjusts the relative base by the value of its only parameter. We've got one parameter. And it's going to be an increment by that value. Okay. And the IP will be +2. So it's going to be relative base plus equal it's basically going to be like this. It's going to be get val IP +1 mode 0. IP +2. Okay, so we've got that. Should we test this on a program? Oh, there's more to this encode stuff. Let's see. Right, so we've done this. Your in-code computer will also need a few other capabilities. The computer's available memory should be much larger than the initial program. Memory beyond the initial program starts with the value 0 and can be read or written like any other memory. Anyhow. how far is the memory? We're going to use hash maps instead of... Okay, the computer should have support for large numbers. Some instructions near the beginning of the boost program will verify this capability. We're using Python, so that's not an issue. So if we're going to use unbounded memory, then how are we going to deal with that? So our memory is... So our memory ranges from 0 to the length of this program, basically. But anything that's accessed outside that so this is a chance to use default dict. So instead of this, we want P to be default dict int. So everything defaults to 0 if it's ever requested. But for ix in enumerate program, we initialize these first n integers into this dictionary. That means they might throw us off by trying to put something in the trillions. Now we don't want to generate all the zeros up to the trillions because that's too much, and that'll be the catch. So this is why we need to use a hash map. It can deal with a number up there without having to create the whole contiguous sequence of zeros. So P I equals X. And then everything here should run the same because we're accessing it using the square bracket parameters, so. Right. Okay. Now what? The boost program will ask... Hang on. The boost program will ask for a single input. Run it in test mode by providing it the value 1. Okay, so we provide 1. It will perform a series of checks on each opcode, output any opcodes that seem to be functioning incorrectly, and finally output a boost key code. So we just put in one number, get out one number. Nice and easy. Right? Alright, let's see if we can get it first try, otherwise we're going to have to test these features. Alright. Running on a queue. So we're going to do... like that. That's how you fetch a result. Putting the number 1, get something out. 203 seems a bit low. It's kind of like in the guessable territory. Not correct. So if we got 203, that means It will perform a series of checks on each opcode, output any opcodes, and finally... Oh! Oh, okay. So if we've got a mistake, then it's going to actually... This 203 just tells us what the mistake was. In fact, we can do this. We'll say for out for O in run int code of that queue. Print O. Let's just see all the results. 203 and then 0. Okay, so 203, what does that mean? So 203, so it says perform a series of checks on each opcode, output any opcodes and the associated parameter modes that seem to be functioning incorrectly. So the opcode is 2. And the parameter, the modes are 0, 3. Wait, what? What's 3? We don't have a 3. Why would there be a mode 3? Or is it the other way around? Oh yeah, no. 3 is the opcode. 0 and 2 are the modes read backwards. That's the way it works. So 3. So it's saying this one here. The So I think the problem really is with this mode thing. Let's see if we've done the mode correctly, because that's really all we added, apart from the hash map thing. Relative mode is similarly to position mode. Wait, so let's remind ourselves what the terminology is. Parameter mode 0 is position mode. Okay. So num plus relative base. I mean, that looks really pretty straightforward. It should just be that, right? Opcode is going to be... Oh yeah, so it's 0, 3, it's opcode 3. And then the 2, it's literally just one mode. Modes equals all of those plus a bunch of zeros just in case. q.get. Oh, opcode 3 is just the one that fetches the input. And puts it in the address. We only can do that once. So... So either we're getting the wrong input, but the input is just the number 1. So it's hard to get that wrong. So it must just be putting it in the wrong place. P IP plus 1. Why are we not... Oh, fuck. Got it. Alright, so now we need to update all these because basically we were skipping modes. This, we were just assuming it was mode 0 all the time because they did say previously storing things will always use mode 0. But now it could be mode 0 or 2. So... the address, instead of IP plus 3, it would be, what we're going to put in there is get val, this is going to be PIP plus 3, modes 3. Not 3, 2. Like this. Because that's like the third parameter, but that's where we're putting the address. We have to do this for everything basically. So here it's the same. 0, 1, 2, okay. Here it's going to be 1, mode 0. Basically it's whatever this number is minus 1. Here we just change IPs. Here it's going to be that. Here it'll be this. Okay. Now, relative offset. Relative base is 0. To start with. But we shouldn't expect it to be 0 when we're... I don't know. Is it 0 at this time? 988. So the relative offset is 988. So instead of getting... So this should give us like position 988. Man, this is confusing. Mode 0. Hello, Blaze Labs. Found you by searching Python. Yes, I think you have, yes. Was it for... It must have been for Advent of Code 2023, which I did in December. Yeah, I'm doing the archived 2019. This month is 2019 has been a very assembly code heavy set of problems. Might have been, yeah. I was gonna ask why so late. Because I started Advent of Code. Let's have a look at the calendar. ...2020 is the first Advent of Code I did. So after that, I was just catching up on all the previous years, starting from 2015. So I'm up to 2019 as an archived year. And then finally, 2021 is an archived year as well, so I'll do that as well. But from now on, all the new years, I'll be doing kind of live. But yeah, I'm trying to catch up on all the previous ones as well. Yes, this is a pretty complex assembly code problem. And it's not working. You can try the example. What are assembly code problems? Well, assembly code language is like a language where you have a bunch of addresses, and each address holds like an integer, a number, and your code just says, just kind of like jump a certain distance through these addresses, I don't know, write a number to this address, add these two numbers together and put the result in this address. All the commands are of that nature. And basically your code kind of jumps back and forth, adding numbers, multiplying numbers, and putting them in certain places. It's a very low-level language, and I mean, people don't normally use it nowadays because now we have, you know, more human-readable languages which can do more complex things. But I mean, Roller Coaster Tycoon, the video game, was famous for having been written in assembly code, which is pretty crazy. Yeah, this isn't Python. I am writing this in Python, but we're simulating assembly code using Python, because simulating an assembly code using assembly code would just be even worse. Assembly is very efficient though. Yeah, to some extent. I mean, it depends what you're trying to do. I mean, if there's some things that just aren't. I don't know. I mean, I've never really touched assembly code in a long time since I was in school, but I would imagine there are some things that are actually more efficient in higher level programming languages because of the way it can do stuff like object orientation and stuff like that. But at the end of the day, every code, every high-level language can eventually be converted to machine code, which is similar to assembly code, but it's even more low-level. So in theory, you can always get the most efficient program by writing it in pure machine code, but nobody does that. I'm not sure if I'd use efficient. I'm sure there's performance gains, but with libraries like C, I can't imagine. Yeah, I mean, if we're talking about efficiency in terms purely in terms of performance on the machine, it is true that the lower level you go, the better the performance. But the amount of man hours you'd have to put into programming, maintaining, testing, adding new features and stuff is so insane. No one would ever really do it. But if we're ignoring that factor, then yeah, it may well be the most efficient, more efficient than Python, but yeah, the irony of you writing this in Python. Well, it's because because we're simulating this, but then we actually need to do stuff which is not really assembly code like. I don't know. Because you need to do some arithmetic outside of the assembly code. You're taking this program, you're running it, but then you're adding these custom instructions, which are, they're still similar to, they're kind of like assembly code instructions, but some of them are. I don't know, they probably can all be translated to assembly code, but you also need to maintain this queue of inputs that you're inserting into the program, and you might need 5 different programs all running concurrently. So they're all separate assembly code programs, but you need to supply inputs to all of them and take outputs from them. All of that stuff is way easier to do with Python code. Right now it doesn't work, and which is annoying because I haven't actually changed much. So it's saying opcode 303, this one is failing. It's really nice that they've actually given us an error code here. So if we're getting this number, I do know the original Orbits, the first way to order airline tickets online, or its precursor, was made in assembly, just because of the massive resource requirements back in the early 2000s. Actually met the guy that made it, he hated it. Yeah, that's not surprising, but yeah. I studied it in school for GCSE electronics and A-level electronics. And, I mean, that was my introduction to programming. And I just assumed that that is all programming. It didn't occur to me that there are higher level languages. Like, I've never been exposed to any. So it made me not want to study computer science or learn any programming until it was I only discovered that there are higher level languages when I was about to graduate in my bachelor's. So I think I'm glad I went maths instead of computer science, really, but the fact that we were shown assembly code in school put me off from the option altogether of studying computer science for bachelor's. So they should really rethink teaching assembly code to. But they probably don't do that anymore in electronics A-level. Actually, they probably do, but they do actually have a proper GCSE course called computer science now, which didn't exist in my day, and I assume they do like Java or Python or whatever in that course. But in electronics, because electronics is, you're literally soldering chips onto a board, it makes sense that you'd still use assembly code there. Sand Knight, welcome in. What do you mean assembly isn't the greatest thing ever? I mean, I found it really cool when I was a kid, but it limited my understanding of programming. I thought that's all there was. So I could visualize how to make a basic, like adding machine or whatever, or a timer, or I don't know, like a number, a keypad. So like someone has to enter their password 3 times or they get locked out, something like that, which we literally put together in assembly when I was studying electronics. But I could not, I did not like the idea of, say, programming Roller Coaster Tycoon in that language, so I never would have gone down that route. I'm just messing around. I saw AD enthusiast struggle with PS assembly and cursing like a sailor. Yeah. I mean, it helps. It certainly helps understanding the Azadream's bytecode. I guess that's one reason I haven't dug into that sort of stuff as much as I mean, it's probably not that complex, because a lot of the Azadream stuff is not actually using the most complicated stuff you do in assembly code. It's mostly just kind of loops. I mean, I've seen some of the stuff. Programmer shared some of the snippets with me before, and it doesn't look that bad. It's just like for example, the map generation is just like in theory, it's an infinite loop that keeps trying over and over again until the map satisfies certain requirements. I looked at that, and that was kind of readable. And yeah, it seems Eric Westel, who made Advent of Code, there were a few years in the middle here where he just loved assembly code problems, and he threw in lots of them. And it seems like we're at the peak. 2019, we're already on our 4th assembly code problem, and this is across the first 8 days, the first 9 days. We're already on the 4th assembly code problem, so I expect there's more to come. He's given an example problem here, so we can probably use this. Let's test it then. Alright, so this is one program, that list of integers. So if we run our program on that, we get the number 109, which is an error code, I think. Oh. What we're expecting to see is the program outputting itself, because this is a concept known as Queen. It's CUNY. This is a computer program that produces its own source code. There's no purpose for this, but it's just something that programming enthusiasts like to do as a kind of like an abstract thing. It's, yeah, I mean, there's it's basically just people do it for amusement, but like in lots of languages. I mean, in Python, in theory, oh yeah, this is what I was about to say here. In Python, this is a quine in Python, literally just the number 1. That counts. Oh. Well, I don't know if it... Well, it's not saying here whether it counts for Python. I guess it's just saying it counts for some languages. But... Okay, but So apparently this program here is a quine. So if we run this on our machine, we only get the 109, but we don't get the rest. Interesting. Let's see if we're getting an invalid opcode. $109. Unexpected opcode 0. Unexpected opcode 0. Okay, I reckon the relative base is just wrong. It should be 0 to begin with. Let's add another 0 there, just in case we're getting something weird. Just a bunch more zeros. That 0 is just padding. Okay, we don't need those zeros. Let's leave 3. Alright, so, I don't know how to even debug this. This is so hard to debug because you can't... I mean, we can look at the... We can see where in the program this happened. While true. Alright. Unexpected opcode. IP. IP is the instruction pointer. That'll tell us which instruction failed. IP 0. What? Oh. No, I got excited there. I thought I realized what the problem would be. It's not just a case of missing out the IP. Wait, what? IP is 0? It failed on the first instruction. Opcode 9 was the first opcode. So IP should not be 0 at this point. Alright, let's go through this step by step. So, this program, the first instruction, you take the last digit, 9, that tells us which opcode to use. We use that opcode. Now this one is a... This instruction says we're gonna change the relative base, which originally was 0. But we're going to modify it by this value here. Get value p IP plus 1 and mode 0. Mode 0 means we look at the next character along, 0. That's 0. So we will actually use mode 0. Okay. Why is there a 1 here? Maybe I've misunderstood what opcode 9 does then. Let's have a look. Adjusts the relative base by the value of its only parameter. So the one is irrelevant. Oh, I see why they put the 1, because they want the 0 to be there. But the 0 will disappear because of the way integers are fetched, so they put the 1 just to make sure the 0 is there. But the 1 is irrelevant. Okay, so you take the 0, that means it's mode 0. So the relative base will be incremented by the next value in P, which is 1. So the relative base should end up 1. Then we increase the instruction pointer by 2. So we skip over that, and then we're sitting here. Okay. So how on earth did we get to this situation? I'm gonna have to somebody is reducing the IP. That's bad. That could happen here or here. All right, let's just make sure this is doing everything we expect it to. So opcode 9, relative base gets increased, IP gets changed. Then afterwards, we should see relative base, IP, and then a copy of program. Let's see what it looks like. 1, correct. 2, correct. And then the P is going to be, let's change this to values. Okay, so 109, 1, 204, so it's going to be the same as, it hasn't modified. Fine. Okay, so that first instruction was done correctly, I guess. Now what? The next instruction is 204 minus 1. Opcode 4 is doing this. So we output this, but we use address mode. And then address mode is going to... so we're going to output whatever we saw before in the list. So it's going to output 109. Okay, it does that. And then it moves on. Okay, so far so good. Then it gets to this one. It's going to be opcode 1. And opcode 1 is here. I reckon we've done this one wrong, but how? P IP plus 3, that's correct. Let's put some more zeros there just in case. It's 3 modes 2. Oh! I think I see the problem now. Damn it. See the problem. Bloody assembly. This is layered wrong. We shouldn't be doing P of... What we should be doing is, we should have is a set val, and it's gonna set whatever is this list location to be this value. This P open bracket is nonsense. It's doing something completely wrong. What we actually need, set val, and it's going to be different from get val. So we need a separate function here. We need set val with a number and a mode. So if it's mode 0, we need key num going to be a number and a mode and a val. If it's mode 0, then enum equals val. If it's mode 1, that is an error. It shouldn't ever happen, so we can take that out. If it's mode 2, then it's going to be enum. We offset it by relative base and then set it to val. Like that. That's what we should have. So here, instead of this, it should be set val, the num is going to be that. The mode will be modes 2. And the value will be everything on the right hand side here. This is the result of this addition. So you can't assume that getting and setting are just the same thing. They're not. They're completely different things. Getting something from an address has a different meaning to setting it from an address. Oh my god, this is gonna... Okay, fine. We can do this one by one. So every time we did this, we actually want to do this. Put a bracket here. And it shouldn't be that complicated because we didn't really do it that many times. And whenever we did it, it was always IP3 in mode 2. So the numbers are probably not going to change. So here, opcode 3. That's kind of wrong. It should actually be... It should be IP plus 1. Why are you putting spaces in? Take those spaces out. Mode 0. you get that. And then what else did we set? All right, this one is similar to these ones, so we can copy this bit here. I'm lost. Where was I? Okay, we're changing the IPs. Okay, this one here. So it's going to be this. Like that. And then here it's the same thing. This. Like that. Relative base opcode. Alright. I don't know. Let's try that. 109, 1, 204, minus 1, 101. Okay, so is it a Klein? Looks like it. Yeah, that's the same program. Yeah, that was... Yeah, setting. You need a special operation for setting. You can't just... Because of the way we're accessing the hash map. Okay. Whatever I was doing before was crazy. I was taking the value and then I was I don't know what it was doing. Alright, so now let's try the other program, the test programs they've given us. So this one. So they're saying it should output a 16-digit number. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Correct? And then this one should output the big number. Alright then, we're looking good. Now let's actually do the actual problem. It's that. Alright, we get that number. Is that all we need? Should be. If it's outputting a number that's already assigned, because if it didn't output one number, if it outputted a bunch of numbers, that's error codes. So if there's no error codes, that means it thinks our program's correct. So that it shouldn't really be any reason that the actual value would be incorrect, but let's see. Correct. Whoa. This program is getting more and more complicated, and we're going to have to keep copying it forward to the later problems. Alright. You now have a complete intercode computer. I hope that's the final time we see that sentence. Finally, you can lock onto the Ceres distress signal. You just need to boost your sensors using the boost program. The program runs in sensor boost mode by providing the input instruction the value 2. Once run, it will boost the sensors automatically, but it might take a few seconds to complete the operation on slower hardware. In sensor boost mode, the program will output a single value, the coordinates of the distress signal. Run the boost program in sensor boost mode. So they're saying literally just run the program with the number 2 instead of 1? Okay. Suspicious. Are they hinting that when they're talking about slower hardware, like we're talking about space age, so maybe slower hardware means our level of supercomputers, so I actually have to identify where the crazy loop is and take it out. I don't know, we'll see. Wait, well, no, don't change that. So, part 2. So in theory, this is correct. It's just a question of whether it will run in time. Oh, it was instant. Well, if this is correct, that's possibly the easiest part 2 they've ever given us. Wow, they were forgiving today. On day 9 of 2019, December. It's literally just change a 1 to a 2. Like, it can't get more simple than that. I'm curious what kind of times people got for this. So, like, for example, this dude, Benedict Werner, solved part 1 in 4:23, and then he solved part 2 in an additional 4 seconds, so it took him another 4 seconds to read that part 2 and quickly change the 1 to a 2. It's plausible. Max Jager took a bit longer. He took like half a minute. 24. He took like 30 seconds. It took me a few minutes. Alright, well, would I stop there? It's 9 done. Take a sneak peek of 10 at the very least. Monitoring station, blah blah blah, something. Oh, it's a grid. Oh, I like these ones. I feel like we can go on to this one. And the stream isn't crashing now, so it seems like we're stable. Alright, we'll go for 10. Alright, it's not an assembly code problem, so it's not horrible to understand for both me and anyone watching, because it must be way worse for people watching, because it builds on like 3 past problems of assembly code. It's really hard to keep track of that stuff. Okay, so 10. Monitoring station. You fly into the asteroid belt. Reach the Ceres monitoring station. The elves here have an emergency. They're having trouble tracking all of the asteroids and can't be sure they're safe. The elves would like to build a new monitoring station in a nearby area of space. They hand you a map of all the asteroids in that region. So that's what the asteroid belt looks like. Fun fact, I was watching, well, one of those QI facts that appears on the QI TV show. Asteroid fields, the average distance between any 2 asteroids in an asteroid field is like, I don't know, like 1,000 miles or something. So it's nowhere near as dense as the movies make it out to be, or video games. Should we look that up? Oh, more than 1,000. When you're in an asteroid field, the average distance between asteroids is like about 1,000,000 kilometers. So you're probably not even going to see an asteroid when you're in the asteroid field. It's there is an asteroid belt around Earth, I suppose, between Earth and Jupiter. So yeah, don't be afraid of asteroid belts. Unless you're like traveling at the speed of light. Even then, the chance of hitting an asteroid must be pretty low. Okay. So it's dot for empty, hash for asteroid. Every asteroid is exactly in the center of its marked position. So they've got XY coordinates. Figure out which asteroid would be the best place to build a new monitoring station. A monitoring station can detect any asteroid to which it has a direct line of sight. That is, there cannot be another asteroid exactly between them. This line of sight can be at any angle, not just lines aligned to the grid or diagonally. The best location is the asteroid that can detect the largest number of other asteroids. Can be at any angle, not just lines aligned to the grid diagonally. That's interesting. Guess you have to try all mounts of stepping. Oof, wow. Oh, okay, fine. This is a number theory problem, really. This might be time for Microsoft Paint graphics. Let's look at the example. I think I get it, but alright, so the best location for a new monitoring station on this map is the highlighted asteroid at 3-4. Wait, they're saying 3-4 is XY, okay. 3 across, 4 down. It can detect 8 asteroids. 1, 2, 3, 4, 5, 6, 7, and 8. Because these asteroids effectively have 0 width. So there is a straight line going to each of these asteroids. The only one it can't see is this one, because the straight line going there directly hits another asteroid. So actually, what you're trying to do is you're taking for each asteroid, you're taking the height and the width, and you're trying to see if they have a common factor. In this case, 1, 2, 3, 4, and 2. 4 and 2. Well, you're not trying to see if they have a common factor. You're trying to see if... You're trying to see if there is any factor such that if you divide both the height and the width by that factor, you find another asteroid. So basically, for every factor, every common factor, you try dividing both. So in this case, 2 is a factor. So you halve the height, you halve the width, and see if there's an asteroid there. There is. Therefore, this is not visible. So that's what you have to do, essentially. Alright, this is a lot of examples, but I think I get it. Just need to go to the toilet quickly, but we'll put the screen on these examples here. All right, I'll be right back. Okay. All right, so problem 10. All right, so we want just some starter code. All right, so for each line, okay, so we just want to make the I reckon we don't actually want to store a grid of any sort. We just want to store a list of coordinates, a list of the asteroids. So it's a set. So we do for row in f.read lines for, so it's going to be for I row in enumerate. So we get the row number. For j car in enumerate row.strip. So if r equals hash, then asteroids add I j. So that just gives us a list of the asteroids, right? Print okay, so that's all the asteroids. I think that's all we need for this. Now, we're trying to find wherever the best location is, we want to find the maximum number of asteroids that can be detected from that location. Okay. We're doing for asteroid in asteroids. For each asteroid, we're going to count how many asteroids it can see. And best equals 0. That's we're trying to see the maximum number. Okay. So for one asteroid, we want to see how many other asteroids it can see. So for every other asteroid, so let's say let's call this A1 in asteroids. For A2 in asteroids. If A2 is the same as A1, just skip this one. So we've got every new asteroid, every other asteroid. We want to now work out, is there anything between them? So basically, there's two ways of going about this. Either we just iterate over all the asteroids again. How many asteroids are there? Like about 1,000 or so. That makes this cubic. Or no, but it's not going to be cubic because the number of asteroids is actually not very dense, so we could do that. So either we go through all the every third asteroid. Okay, we'll try that. If it's too slow, there's another way, using prime factors. So for A3 in asteroids, all right, so we've got a third asteroid. Well, we want the delta values, so di equals A2 0 minus A1 0. That's the deltas. So for each third asteroid, we want to know if these 3 points are collinear. They're all in the same line. In other words, the gradient from A1 to A2 is equal to the gradient from A1 to A3. So what we're trying to say is let's say EI equals the gradient, the deltas for the A3. So it's going to be A3 0 minus A1 0. EJ equals A3 1 minus A1 1. So we're trying to say if EJ basically we're trying to say if EI you have to watch out for the infinite gradient though. So let's handle the infinite gradient first. So infinite gradient is where we go straight up or straight down. I mean, look, the general case formula looks like this. We're trying to say the gradient, so the height, EI divided by EJ equals, I'm just writing in maths speak, not in programming language, DI divided by DJ. So if you cross multiply, you get EJ times that, and DJ times that. So that's what we're trying to say. But if the DJ is 0, or the EI is 0, will that still work? So if DJ is 0, so basically, yeah, if DJ is 0, then EJ would have to be 0 as well. Also, A3, we need to make sure it's not equal to A1 or A2. So we're saying if this holds, if these two are equal, then, so if DJ was 0 and EJ was 0, 0 equals 0, so that's true, so that's fine. So in this case, they have the same gradient. The last thing we want to check is, okay, if they have the same gradient, we want to see if A3 is between A1 and A2. And that would happen if, basically, if so it'd be I is like strictly smaller than DI, or EJ is strictly smaller than DJ. Ah, but wait. What if they're negative? Ah, hang on. Okay, we have to account for, okay, so if DI is greater than 0, and I don't know, if DI is greater than 0 and DI, so that's one condition, or DI is less than 0 and so it's less than 0 but greater than DI, so it's between them in that direction. Or the third case is if DI equals 0, in which case we have to go to the DJs and so either we have to go to the positive case, so we have to do it like this. Well, we don't have to have this condition. We can write it like this. If it's this way around, or this way around, or it's just try all four. I don't really know which ones are redundant. Just do it like this. EJ, DJ, or 0. No, this is wrong. Wrong. Hang on. We have to have all these simultaneously held, because one could be positive and one could be negative. So you don't want an or condition. What you actually want is if 0 is less than or equal to EI is less than or equal to DI, and so it's going to have to be this. This or 0 is greater or equal to EI is greater or equal to DI. And basically the same for the J's. So either it's sandwiched between those or sandwiched between them the other way. And it has to be sandwiched between the J's as well. Those both have to code. If that happens, that means it's not visible. So we continue. So if we reach this point, then we found a visible asteroid. No. What? Ah. We break. We break out of this loop. So else, if we didn't break out of the loop, that means we're safe. This is actually visible. If we get this far, then A2 is visible. All right. And then if we do all of that for A1, we know how many are visible to A1. We can say best equals max of best visible. I don't know if I've got this formula correct. Might have to think about it a different way because it's just too confusing otherwise. It's gonna take a while because there's quite a lot of asteroids. Well, it's cubic. Okay, Iran, 278. Not correct, it's too low. Curiously, it's the right answer for someone else. Nah, I mean, for low numbers, that's bound to happen. Alright, fine. I have to test it on the examples then. Test it on the most basic example. So there's 10 asteroids, and we're saying the best is 7. 7 visible. It's saying it should be 8. Interesting. I think so. We've had one case where we've regarded it as being invisible when it was actually visible. Print. Oh, okay, whatever. Just print EI, DI, DJ, EI, EJ. So these are the ones we think are in the way. Why is it printing so much stuff? Okay, this is weird. Oh, because we're trying all the different asteroids. Alright, let's stick to asteroid 4-3. Eight. We got 8. What? Oh, for goodness sake, I'm printing visible and not best. So we got the correct answer there. It probably was correct all along. Okay. $348. 0? Wait, what? 0? Damn it. How could that happen? Wait, I didn't change anything. Any logic, did I? Oh, of course. Whoops. Take this out. Alright, let it run again. It should take the exact same amount of time. We just stored it in the wrong variable. Best is what we're looking for. So we just outputted some arbitrary number of visible asteroids. We want the best one. 299. It's only a bit higher. Just, I guess, makes sense. Correct. Alright, once you give them the coordinates, the elves quickly deploy an instant monitoring station to the location and discover the worst. There are simply too many asteroids. The only solution is complete vaporization by giant laser. Fortunately, in addition to an asteroid scanner, the new monitoring station also comes equipped with a giant rotating laser perfect for vaporizing asteroids. The laser starts by pointing up and always rotating clockwise, vaporizing any asteroid it hits. If multiple asteroids are exactly in line with the station, the laser only has enough power to vaporize one of them before continuing its rotation. In other words, the same asteroid that can be detected can be vaporized, but if vaporizing one asteroid makes another one detectable, the newly detected... Fine. I get it. For example, consider the following map, where the asteroid with the new monitoring station is marked X. The first 9 asteroids to get vaporized in order would be these. Alright. The elves are placing a bet on which will be the 200th asteroid to be vaporized. Win the bet by determining which asteroid that will be. What do you get if you multiply its x coordinate by 100 and add its y coordinate? So... Okay. So we now start from this location we've decided. Are we? Wait, what? Oh, we need to actually give the location. Alright, let's just do that first. Right, so that's part 1. And we should get the best asteroid from that. Let's run that again. $29.26. So that's the asteroid we're going to use. So there's different ways we could do this. I reckon we should just say we do a while loop. So so they said the starting direction. So the starting direction is what? Directly up? Okay. So let's say starting angle is gonna be the -1, 0. That's the I value going up, so up the row and 0 across. Now, starting from that direction, we want to rotate clockwise until we come to across to an asteroid. The catch is, though, on the first iteration, we're allowed to shoot the one ahead of us, but from then on, we're not. All right. So I reckon we should just list all the asteroids in terms of okay, so we take 200 shots. Okay. Doesn't matter what the iterator is. So in each shot, we're gonna turn until we're gonna list all the asteroids in order of angle and distance. And the asteroid we shoot is the one with the minimum angle and the minimum distance. But on the first turn, we're allowed to shoot what's ahead of us, which is annoying. But then from then on, we don't. So, we just have to do a special first move, I guess. If there's something directly ahead of us. Okay. For A in asteroids. If okay. Oh my god. Let's just take a list of all the asteroids which are in this direction specifically. Just make a list here for A in asteroids. If okay, just do the usual. Di equals A 0 minus well, we best asteroid, so let's just say AI AJ equals best asteroid. Should we just put everything on the origin now? That'll make things easier. So just asteroids equals set. It's gonna be A 0 minus AI. So we're normalizing, so we're going to start at 0 and everything is just relative to us. A1 minus AJ or A in asteroids. So this is a new asteroids. That we can just say because now we've normalized. Don't need to print that. We can remove the origin. That's where we're standing. Direction -1, 0. Okay, this is better. All right, so For A in okay, we've already done this. Hang on. For A in asteroids, so we don't need deltas anymore. Okay. Or for A, I, A, J in asteroids. So this is the delta. Okay. If so we're trying to say if this is the starting direction. Well, okay, let's just... We're starting looking up, so let's just say if AJ is 0, and to hardcode this, I can't be bothered to generalize it. Okay, AJ is 0, and AI is less than 0. That means it's above us. Then hands dot append AI J. Okay, so we just put all the things that are above us in cans. And now, if cans by the way, let's put steps equals 200 to begin with. All right, so if there are any candidates, we must now pick the one with the smallest AI value. In fact, just put the AIs in here. But these are negative. So you actually want the biggest. A equals max of cans. So that's going to be the biggest negative. Zero. Asteroids dot remove A. So we destroy that one. And then we decrease steps by 1. So if there weren't any asteroids up there, then this doesn't happen, and we use 200 steps instead of 199. Okay, fine. So that's the annoying first step. I don't know a way of generalizing that nicely. But now we always take the next asteroid along. We don't look directly in our direction. Oh dear. Let's just check that this actually does something. So we deleted -30. Okay. That's good. Right now, we just need to figure out how to find the next one along. So first, we want to find of all the asteroids. So we currently have an angle, a direction we're facing. Right? And we need a method here. In fact, this would be simplified if we had a method here. Let's see. Define get clockwise rotation for a given asteroid. So given our facing direction and a given asteroid. We want to see how much we need to rotate to reach that asteroid. But that's not quite it, is it? It's going to be a floating point. That's the problem. And we can't really compare floating points easily because we... I'm not good with this basic geometry stuff. Alright, just do it as a floating point. So what is the clockwise angle between two vectors? Can we just look this up? Alright, dot product is what we're going to use. Of course it is. We want range 0 to 360. Alright, so we need this. Essentially dot equals, so it's going to be direction we're facing and the asteroid. So it's going to be D1, D2 equals D, A1, A2 equals A, so it's going to be D, D1, wait, what? Is this correct? Dot, det, okay, fine, yeah. So the X is replaced with D's. And the Y is replaced with A's. A10 to, yeah, we're going to import that. The angle is that. But because we don't want it negative 180 to 180. We actually want it 0 to 360. So they're saying add pi. Wait, do this. Okay, that's weird. Okay, do negative det, negative dot, plus math dot pi. That probably is correct. I just can't visualize that in my head. return angle. All right, let's try using this then. So basically want to find we're going to need a float equals thing as well. Float equals. X and Y. Return absolute value of X minus Y is less than or equal to, let's say, 1. I don't know. Probably that's small enough. All right, so we're saying okay, if any so we want the get clockwise rotation between our direction and an asteroid to be 0. So we're saying float equals .0. So if any of them are close to 0, for A in asteroids, we want to take the one with the minimum distance to us. So A equals minimum of asteroids E equals lam. So this needs to be A or A in asteroids if its angle is 0. E equals, and then we need the minimum, like, minimum key equals lambda A maps to the norm of it. Oh my god, this is getting too complicated. A equals that. So before we have -3,0. Let's see if we get the same one out. Print A. Asteroids dot remove A. Steps minus equal 1. Okay, this is using the angle now. Let's try. 299. We didn't find one. I'm gonna have to print the angles. I don't know if this is doing what we wanted to. Hello, Rodol Job. Alright, we've got a bunch of angles. Are any of them effectively 0? Oh boy, math stuff. I got a math test on Friday. Does your math test include geometry? Because this is confusing the heck out of me. Includes virtually everything. What level of math test is this? Is this school or undergraduate? High school and tests. I don't know what it might be in your country. Oh, I see. Okay. In the UK, we have GCSEs. I guess that's the equivalent. Why are we printing? What the? If D2 equals 0. Oh, not D. We want A2. D2 is 0. It's always 0. Didn't want to guess between UK and US. Well, I don't spend much time in the UK, so I probably have a merged accent. 3.1415926535897. Okay, we get exactly pi. Interesting, but that's not the angle we wanted. We wanted... maybe we don't need to add pi then. Don't add pi. We're getting this in radians. Okay, don't add pi. So we should be getting angle 0. Okay. Now output the A's. We should be getting all the A's which are directly above us. You're adding pi. Normally pi is used to multiply stuff, never as addition. Well, it is used as addition here as an offset, because we're counting the amount of angle we've rotated by. But if you use inverse tan, Some programming languages will be off by pi because they decide to restrict to the range plus pi to minus pi, but some decide to do 0 to 2 pi. So if you want to go from one range to the other, you have to add pi or subtract pi. I didn't know which one Python was, so I added pi, but it turns out Python is going 0 to 2 pi, so we don't need to add pi anymore. Well, this is interesting, except why... Okay, these asteroids are above us, and they got an angle 0. These asteroids are below us. They've also got an angle 0. We wanted the angle to be 2. We actually want the angle to be 2 pi, not 0. Right, let's try doing the original formula that they gave us. A tan 2 det dot. Because we just want to get the things which are above us, which should be angle 0. That's basically what I'm trying to do. It's on paper, it's probably not that hard, but okay, now we get these. But we get 0, angle 0 for these. Negative ones should be 0. Positive ones should be on the other side of the plane, so it should be 2 pi. Why? A tan 2. So A tan 2 gives 0 either way. Well, I suppose that's probably correct. But A2 is equal to 0. If A2 is equal to 0, doesn't that mean that the pass parameter A is also 0? Or is that fine? So A is a pair of coordinates, A1 and A2. So we're just interested in the angle in the vectors where A2 is 0. A1 is essentially the y value. It's kind of, I've done it the other way around from x and y's. So if A2 is 0, that means this asteroid is above us or below us. So I want the angle, and the angle should be 0 for the ones that are above us, and it should be pi for the ones that are below us. That's all I want to get out of this formula. But what I get is 0 in both cases, which is halfway there, but I don't remember my geometry to know how to get what I really want. I just basically want the angle. So we have a vector D, which is where we're facing. And I want to find the angle, the clockwise angle until we get to A. That's literally all I'm trying to find. I can't even figure this out. So the formula I'm using here is the dot product. And then inverse tan of... Oh my god, I've done the formula wrong. Oh. I see. Hang on. So I'll copy the formula in again. Yeah, I got the wrong... So this is how it was on the Stack Overflow page. All right, I didn't copy it in correctly. So x1, y1 is d1, d2. That's a bit confusing because I've got d's here, but I've got x's and y's here. So x1 is d1. So every x1 should be changed to d1. Okay, done. Now y1 is d2. So every y1 should be changed to d2. Done. x2 is a1. y2 is a2. So that should be hopefully the right formula, but we now might be off by pi. Let's try. So whatever we had before, I don't know what that was, but it was something strange. So for the positive ones, we get pi, and for the negative ones, we get 0. Exactly what we need. Yes. So of all those, we pick the one that's closest to us, -3. All right, we're one step closer. So now let's put this all together. So what we're trying to do here is we have a laser. It has a direction. And every step we rotate until we see an asteroid and we destroy that asteroid. So we're trying to find the asteroid with a minimum angle, but that angle is not allowed to be 0. Because the problem says we have to turn a little bit at least. So each step, we're not allowed to shoot what we're looking at. We have to turn a bit and then to shoot the next asteroid. Okay, so basically it's similar to what we did before. So A is going to be the minimum A for A in asteroids if the rotation from us to them is not 0. So it has to be strictly above 0. So it could be a little bit above 0, but it can't be 0. So we pick the smallest one, i.e. the one that's closest, the next in line. And amongst all of those, we choose the one that's the closest distance to us. So we want key equals lambda. For a given asteroid, we map A to its get clockwise angle, followed by its norm. Because all the asteroids which are in a line, we want the one that's closest. Oh man. Okay, so that. Do that. So out of this, we should get an asteroid, right? We print A just to see what it is out of interest. We remove it from the asteroid field. We set our new direction to be looking at that asteroid. Now, just run that. Ultimately, what are they asking for? They're asking for the 200th asteroid that's going to get vaporized. All right, so now we're killing lots of asteroids. That's cool. So the 200th. So if we do this 200 times, or 199 times, because we do one step for this weird thing that we do at the start. Then the resultant direction should now be whatever that last asteroid we destroyed was. Oh, bollocks, but it's... Oh, we gotta calculate the offset. Because we offset all the asteroids, so we have to put it back where it was in space. Where did we offset? Okay, we offset here. We removed best asteroid. So now we have to add best asteroid back. So final equals final x equals, it's going to be A1 plus best asteroid 1. Final y equals A0 plus best asteroid 0. And then what they want us to do is just do a little arithmetic, to multiply x by 100 and add y. Okay, print 100 times final x plus final y, just to encode it. All right, what do we get? Please give me the right answer. $1404. Nope, it's too low. All right, so we can try using their example, see if we get the same answer as they do. So this example. So we should get 11, 13, 210 asteroids to start off with. So there's 300 asteroids altogether. Wait, why are we still get? Oh no, okay. It's 210 asteroids visible from. We didn't print. We're saying the final answer is 1401. Should be 802. Alright, so I'm gonna just print out what asteroid I'm deleting at each step. Maybe we can just compare it with what we see. Right, so put the best asteroid here. Alright, let's see what it does. Why am I using direction? It shouldn't matter, but... Why am I using A, I mean? I should be using direction. Let's see if we get the same answer then. But that shouldn't affect it. Okay. So the first thing we said was 210, 13, 11. That's correct. Well... Sort of. They had it the other way around. They said x equals 11, y equals 13. Yeah, because we're doing it the other way around. Okay, fine. So we're saying the first thing we destroy is 11, 12. Correct. Then 12, 19. They say 12, 1. So this is... Now let's do the clearer example, this one. Actually, that example is not very good. So why did we get 12, 19? And so the first asteroid to be vaporized is at 11, 12. Uh-oh. think I might have X and Y's the wrong way around or something weird. Hang on. Let's try this, do this formula one more time. Yeah, I think this is a bit weird. Okay, so, because their notion of Y is positive in the up direction. We should be using X's and Y's because it actually matters. I thought it wouldn't matter, but it does matter. Because that defines how you're turning clockwise. That defines clockwise. The term clockwise doesn't make sense if we don't have the same frame of reference here. So I've been using rows and columns, but it's a bit different. It's inverse of. So we've actually been taking the 1219 because it was the opposite way around. All right, let's try and fix this. All right. So x1, x2. So they're saying dot product between this and this. Right. The x value of our first thing is negative d2. d2. No, sorry, no. Yeah. No. It's d2. Positive d2. d2 was the row, the column, and that matches x. y1 is actually negative d. Wait, we change all the x1s to d2. Okay. y1 is negative d1 because d1 is the row, and as you go down rows, you're actually decreasing y. As you increase row number, you decrease y, so we actually had to turn this around. We would say negative d1. We should have just used x and y's from the start. Now it's just a mess. Negative d1. All right. Similarly, x2 is a2. And y2 is going to be negative a1. Now, do we have to change anything else? If this is correct, then we haven't actually used coordinates anywhere else. We've just sort of been using, just trusting that formula. So let's see if that changes things. $11.12. We still go for $12.19. I feel like there's still something else we have to change somewhere. Okay, so this step is fine. This step is where it goes wonky. I'm saying it's not equal to 0. Trying to minimize. Why did we get the same result? I thought that would turn things around. So direction is -1, 0, directly up. Should we just change all rows and coordinates all to Cartesian, just so that we don't have as... I don't know. Excuse me. So the first move is correct, 11, 12. And then they're saying 12, 1. We're saying 12, 19. What? 12, 19 is really far away. Why is there no 12, 1? Oh, bollocks. It's because 1219 happened to be... Because of the floating points, it's happens to be... smaller angle. Wait, what? No, that's not it. Oh my god. No, that's not the issue. So in the large example above this, okay, starting from here, they're saying we're at 11, 13. And we want to destroy 11, 12. That's 11, 13. I want to destroy 11, 12. Wait, what? Which way round is Y? Oh, Y is the other way around. Fuck. Y actually matches our directions, so we need to change that again. Oh, God. So these are not negative. Wait, which ones are not negative? Yeah, these ones are not negative. They are actually going from the top down. So we go 10, 19. What? Alright, are we closer to the correct answer? The problem now is that wait, 10, 19. So 11, 12. 10, 19 means we go one left and a lot up. gone the opposite direction. Clockwise direction. Let's try this out. Print get clockwise rotation from 11, so it's going to be from all right, screw it. Let's change this all to XY coordinates. This is an absolute mess. Okay, first, let's convert all the asteroids to XY. So before it was row column. So we just swap it around. So it's going to be A1, A2, no, A2, A1, or A1, A2 in asteroids. Okay, just swap everything around first. Okay, so that's going to reflect what it looks like on the in example. So now it's X's and Y's. Swap this one around as well. Best asteroid equals best asteroid 1, best asteroid 0. Alright, so now this is X and Y's, this is X and Y's. Now we can do set A0, what? A0 minus best asteroid, A1 minus best asteroid. Okay, normalize. The direction is going to be 0 minus 1. Oh my god, the direction was wrong. Everything else is probably right. Okay, but anyway, we're in X's and Y's now. So now this is X, this is Y. So one more time we do this formula. So we're changing, so X1 is just D1. So it's just going to be X1 is changed to D1. Y1 changes to D2. X2 changes to A1. Y2 changes to A2. Turn angle. Okay, don't do that. So then do all this. We can just, I don't know. Alright, and then we print... So whatever the A is, we don't need to swap these around now. Keep them like this. And copy that line. And then finally, this is going to be zeros and ones. All right. Let's see if we get different numbers now. Still? But we're using X's and Y's now. So we're at 1311. So 1019 is to the left and up. That's a negative angle. What the fuck? Oh, maybe we have to do this pi thing. Maybe, hang on. Hang on. Alright, let's test this then. So, print, get clockwise rotation. So it's gonna be from, 0, 0, -1, 2, so this one's going to be -3, +8. That is the vector. So we would expect this to be negative. I bet it's positive. It is negative. Oh, no, it's correct, it's negative, but that's why we added pi. Fuck's sake. We do minus that, plus math dot pi. Now try it. It should be now in the range 0. So it should be really high now. It should be like 3.5. Yes. It's in the range. It's larger than pi. Okay. So we get 12.1, 12.2. So we're saying 1009? No. But we are getting 12.1, 12.2. Where's 11.12? Why didn't we eliminate 11.12? Right, so take this out. That looks like the right angle. Is it though? Hang on. -3 +8, but +8 is actually down. Oh. You know what? This formula is assuming y is going up, isn't it? So D2, we have to actually make all the y's negatives. This is so confusing. And I've made it confusing for myself because there's like 3 different frames of reference here. One that this formula is assuming, one that they're using on the site, and one that I started using myself, and now I'm juggling these 3. So probably have to negate all of those. Okay, try now. Because this clockwise rotation only makes sense for... No, now it's even more wrong. I can't figure this out. Go back to not having this. Oh, maybe you have to. I mean, this is a bit weird now. So, because you've got minus minus here. Just, I don't know, put all the minuses in brackets just in case. No, that doesn't change it, but anyway. We're back to this again. Can't. It's just so stupid. Alright. We know that if you turn like this, it should... Okay, let's give ourselves something. 0 minus 1 is looking up. Right? 0... So if we do 1 minus 1, that should turn a little bit to the right, clockwise. So if we get the right angle here, it should be like 45 degrees, shouldn't it? No, it's negative. So this formula is all wrong. So if we did minus that, let's try that then. No, we want to add pi. So that's between 0 and pi. Is that half a pi? No. What are we expecting? It's, look, we're going up, and then this one is 1 across, 1 up. So that should be exactly pi by 4. No. Yeah. Pi by 4. So less than 1. Why is it so hard to just get a clockwise rotation? Like, should I just negate that? Some combination of negating and whatever has got to give us the right answer, right? I don't know. I don't know how to get the... I don't know what the formula is for the clockwise rotation. I can't figure it out. Yeah, we don't want to do that. So why is this giving us a negative number? I don't understand. Angle is that. Let's find another formula. Use a different formula because I don't know if this is even correct. Dot product determinant. What are we expecting it to be? Pi, what is pi by 4? 0.78. So we actually had it, the right angle, if we went with negative that, but that is negative pi by 4. What did we add? I'm just throwing numbers in here now. Add pi by 2. No, I can't do it. A whole bunch of different. I'm looking at the Stack Overflow. Everyone's giving a completely different answer. Let's Google it again. Just find a different. Calculate the angle between two vectors when direction is important. Arctan to x1. x1, y2. So that's x1, and that's... They're saying something different here. Okay, they're saying... So this site is saying this. Oh, okay, so if I were to do that, we want the det. Oh no, that was right. That was the det, not the dot. So it'd be x1, y2, but we negate it because it's negative, minus y1, negated, x2, yeah. And then the dot is x1, x2, plus y1, y2. So that matches what they're saying. All right, well, I don't know. What about this? 0, -1 to 0, -1. It should be 0. If it's not 0, then... it is 0. So if we go 1 across... we're expecting the angle to go up. It goes negative. Okay. How about if we go 1, 0? It's pi by 2. Should be pi by 2. That's negative pi by 2. And we go 1, 1. So it looks like it's just the negative, but it's... and then finally, if we go 0, 1. So we flip it. What do we get? Should be pi. No, but now it becomes positive. Alright, so let's do the fix they suggested. They suggested do this, this, plus math.pi. Try that. We get pi. Alright, go back to 1, -1. What is this? This is upright, so it's turned by an angle of pi by 4. Why is it what is this? Pi plus pi by 2? Oh my god. I mean, you get a positive sign for... Hang on. Okay, they're saying this is actually for computer graphics, so it should be X pointing right and Y down. So I should have just used... Well, they didn't say that to begin with. Later on, they've said they did this using a left-handed coordinate system. So Y is down. Fine, but that's still... Okay, fine, we'll try that then. So in that case, it's actually not negated. Don't negate anything. So that should be clockwise. They're saying that that should be clockwise. That sounds about right for that. So if we go to the next one, so now 0, 1. This should confirm it. This should be pi. Yeah. And then just a bit more. Wait, okay, so and this should be 0. Or are they going to choose 2 pi? Because that's an issue. It's 2 pi. Ah. If that might be the issue. 0 was equivalent to 2 pi, but we don't want it to be. If float equals angle 2 times math.pi, angle equals 0.0. Like that. So just convert 2 pi to 0. 802! Don't tell me that was the problem all along. I don't think so. There were other problems like the signs and stuff. I made an absolute mess of this. Let's see if this actually works on the bigger one then. One 419. What was it before? 1404. So we're just going for a few more. Thank goodness. Oh my god, I hate Euclidean geometry. Well, I hate basic geometry. The irony is that complex geometry is actually easier because you abstract away all these coordinates and stuff, and you're just dealing with like generic vectors called v and cross products and dot products, but you don't actually look at the individual coordinate systems and stuff. It's been a while since I studied differential geometry, but it's all these basic high school vector stuff that's the most confusing. And I mean, the problem with the formula that was given in the this is what I was looking at. But the problem with the formula is it's not unique to the language, because some languages have different implementations of atan too. So down here they say sometimes you have to adjust like this, minus det minus dot plus pi. Oh man. Alright. Done 10. That's enough for today. I'm really hungry and it's 8:30 and I meant to get food long ago. Oh dear. Okay. Nasty problem. Don't like geometry. Okay. Finish there. But you gotta know it for these problems. Alright, so that's problem 10. We've done the first 10 problems. That's pretty good going. We're like a third of the way there, I guess. Yep. And if anyone watching wants to join my leaderboard, here it is. The code is, well, I'll paste it in the description, but it's also here. All right. Thank you for watching. See you in maybe a couple of days' time. And we'll continue with this, and we'll try and get 2019 TikTok. All right. Goodbye.